Now, I would like to
Madam, please unmute yourself.
Sir, automatically mute हो जाए.
Recording in progress.
He holds an MS Engineering in CSC from USSR and a PhD in Computer Science from JNTU. He had served as Associate Professor at SIT and Executive Council Member at Dr. B.R. Ambedkar University. He have guided 42 research scholars to PhD and published over 130 research articles. We would be delighted to hear your insights on the STP program, sir.
Good morning to all of you. Thank you, madam, for your brief introduction. First of all, I would like to welcome all the students and the researchers and also faculty members of India and also the abroad for this international online short-term training program on recent advancements in fuel cell and hydrogen storage that has been organized by Department of Mechanical Engineering, Professor Chalapati and his team in collaboration with Federation University, Australia. So once again, I welcome you all. I hope that you'll all enjoy this workshop, short-term training program. And today there is a need, though I'm a computer science man, but I know little bit of what the need of what hydrogen storage, because this hydrogen storage is very much important, because this generation we are generating a lot of pollution in terms of various things, maybe in terms of vehicular movement, or maybe in terms of plastic, or in terms of usage of ACs, etc. So if at all we have something kind of hydrogen storage, at least we can give to the next generation purified water, purified air. These are all the two things we need to give for the next generation. So definitely this short-term training program, I hope will enlighten on these aspects so that you can communicate with your colleagues and also you can communicate this proceedings of this short-term training program to your students and also to your colleagues from other departments so that people can carry forward this program. So once again, I thank the organizers for inviting me, and also I request all the I request all the participants, you need to, after this short-term program, training program, you need to develop your own communication skills between all of you so that tomorrow those who are going to work in this, at least you can store, you can save, you can share your thoughts with the other, with other colleagues of this training program. And I hope all of you will enjoy this program. Thank you. Thank you.
Thank you, sir. I would like to introduce Professor K. Srinivas Chalapati, sir, Head of the Department, Mechanical Engineering. He has a huge experience of more than 20 years in academics and 2.5 years of industry. His research interests are in the automobile exhaust pollution control and the different methods and technologies involved in it. He is the student section advisor for ASME, Anurag University Student Section, and also member ASME, American Society of Mechanical Engineers, life member ISTE, in charge director Anurag University Foreign Relations Office. We'd be grateful if you could shed light on the importance of this STP program, sir.
Thank you, madam. Good morning, all the participants from various states and various countries. I would like to welcome you all for the first international online STTP on recent advancements in fuel cells and hydrogen storage, organized by the Department of Mechanical Engineering, Anurag University, Hyderabad, India, in collaboration with the Federation University, Australia. We would like to organize such kind of the STTPs and FDPs for the benefit of the community, the mechanical engineering in specific, to enhance and to inculcate the research and development R&D activities among the students and among the research scholars, among the faculty. And this fuel cell and hydrogen storage, which is the upcoming and future for the automobile industry, and not only maybe automobile industry, not only just automobile industry, it may be extended to other areas of the mechanical and energy fields. And especially the fuel cell, which we are going to get in more insights by our distinguished speakers, which is the made for the net zero emissions, and which is the feature for the researchers on pollution control, and then the automobile exhaust emission pollution control and engine developments or fuel developments, alternate fuel development. And of course, there is a lot of research is going on in the hydrogen storage and fuel cells in and around India and abroad, and all the majority of the countries are doing the research in this. Especially the hydrogen, as you all know, is the cleanest fuel among all other fuels in the globe. And if we can have a better storage for the hydrogen, then definitely, and that too safest, then definitely the future of the automobile industry, and when compared to or in comparison with the EU norms, definitely the automobile industry will develop and will grow, will have more advancements and more advantages from this hydrogen storage research. And in this regard, the Department of Mechanical Engineering, Anurag University, is also doing a lot of work, and best work is going on in our department and in collaboration with the IITs and NITs. And we have recently published a research paper on the fuel cells and hydrogen storage in a journal with a very high impact factor of 7.139, which is also a good achievement of our researchers, of our faculty in our department. And as a part of improving the research and inculcating the research thoughts in the faculty, the Anurag University is giving the seed money funding to the faculty. We propose, and based on the worthy of the proposal, the management is giving the seed money to do some research. And recently, one of the organizers, Dr. Jiptesh, got the seed money for 4 lakhs to develop that means to curb the emission controls, that means to develop a device for doing the emission or to reduce the emission control of the automobile, especially diesel. And in that regard, in this process, the fuel cell and hydrogen storage is also being introduced as a course in our 4th year mechanical students, and almost 150 students have opted that subject, and they were very happy learning about the different advancements in the fuel cell and hydrogen storage. And this international online STTP will definitely give you more insights about the fuel cells and hydrogen storage, and more we can get the knowledge from our distinguished speakers and keynote addresses by Dr. Jin Peng and Dr. Shubhi Sharma. And I thank both for giving us this opportunity and collaborating with us and accepting our request for collaboration and doing and organizing this STTP. So I once again welcome you all for the international STTP on recent advancements in fuel cells and hydrogen storage. And thank you and have a good day. And I wish you will have a better knowledge from these 5 days, in these 5 days from this STTP. Thank you.
Thank you, sir, for sharing your insights. Now, with great excitement, I would like to introduce Dr. Shubhi Sharma, Associate Professor, Hydrogen Technologies, Center for New Energy Transition Research, Federation University, Australia. Professor Surabhi Sharma has completed her doctoral degree from the University of Ulster, United Kingdom, where she explored synthesis and electronic properties of graphene oxide and its use in supported anode electrocatalysts for direct methanol fuel cells. Soon after, she joined the University of Birmingham, working as a research fellow at UK's first EPSRC-funded Centre for Doctoral Training in Hydrogen and Fuel Cells. Here, she developed fuel cell-specific research and delivered postgraduate teaching in the area. She also delivered successfully as the work package leader for the EU project STAMPEM 5.2 million euros 2012 to 15 under the Fuel Cell and Hydrogen Joint Undertaking Framework Program 7, working along with 5 EU-wide industry partners to develop corrosive protection conductive coatings for PEMPC bipolar plates. In 2017, she moved to the School of Biosciences, University of Birmingham, working as a research associate and co-investigator of DSTL-funded multidisciplinary synthetic biology project. She joined the Center for New Energy Transition Research at Federation University as the Associate Professor of Hydrogen Technologies in 2022. She has supervised many doctoral and postgraduate research projects. Some of the projects were funded by the agencies such as Science Without Borders, Brazil, EPSRC UK, EU, FCHJU, and Australian Carbon Innovation, ACI. She has published over 35 peer-reviewed papers, several conference papers, 2 single-author books, and contributed to book chapters. She also serves on editorial boards of high-impact, high-visibility journals and as a grant reviewer for funding agencies such as EPSRC, UKRI, and ACS. Her research interests include development of graphene oxide, 2D and 3D nanostructured carbons, and hybrid materials for application in fuel cells, including electrocatalysts, proton conduction membranes, and coatings. She is also interested in other electrochemical systems, including Li-based, lithium-based batteries, and biosensors. Other areas of interest comprise upcycling of carbon resources and biowaste for energy, fuel, high-value carbon nanomaterials, synthetic microbiology, and development of microbe-assisted electrocatalysts. Your unique experience in hydrogen technologies would be highly valuable. We would be grateful if you could shed light on the importance of our STTP on fuel cell and hydrogen storage map.
Thank you very much. Are you able to see me?
Yes, ma'am, clearly, you could say.
Thank you. I'll try and share my screen now before I say anything else.
Yes.
Am I allowed to share my screen?
Yes, madam, you can share your screen.
Okay. Thank you. Can you see my screen yet?
Able to see your screen, ma'am. Please make it, yeah, now you can see. Yes.
Okay. Can you see the main screen?
Yes, madam.
Is this better?
Yes, full screen, we can see your screen.
Okay.
Thank you. You can go ahead.
Thank you. Thank you for inviting me to this short-term training program. I really appreciate my involvement in such a program. It's an honor to be able to participate and deliver to a global audience at such a platform. And I'm grateful for Anurag University to approach us for this collaboration, and hopefully we can do more good work together as well in the future. So today I'll be talking about PMFC components and their limitations, and a little bit into the possibilities for next generation systems and how the different components need to be investigated or improved in terms of their structures and possibilities of performance and durability related issues. Before I begin further, I would like to acknowledge the traditional custodians of the land and water where our campuses are located, and we recognize their continuing responsibilities to care for the country. At these sites of teaching and learning, we pay our respects to the elders past and present and extend our respects to all Aboriginal and Torres Strait Islander First Nations people. In particular, I'd like to acknowledge the Gunai Kurnai people on whose land I am today based and giving this lecture from. So the presentation that I've prepared is focused on giving information on fuel cells to a broader audience, and I tried to keep it such that it can cater to those who are beginners and those who are also having some background knowledge of the systems. So I'd start with a short video of what fuel cells are and what are the different components that go into a fuel cell. A typical fuel cell has a variety of components within it. There's bipolar plates at gas diffusion layers, microporous layers, and catalyst layers, along with a membrane at the center. Hydrogen flows through at the anode and oxygen flows through at the cathode side, where each of them reacts with the catalyst and is broken down further. Electrons are generated from the anode and go from the external circuit into the cathode, generating current, whereas the protons pass through the membrane into the cathode and then react with the electrons and the oxygen on the other side to form water. And that's the basic operation for all fuel cells. Oops, I'm sorry. So that's the basic operation for all fuel cells. Now, fuel cells have a variety of are in competition with a variety of other electrochemical systems right now. Batteries are some of the main competitors, and there are supercapacitors and capacitors, and they're often compared to these different electrochemical systems. Fuel cells, because of their various specific features, they do stand out in a number of ways, given the fact that they have a wide range of operating temperature, which is particularly useful for a variety of diverse applications and being suitable for both stationary and mobile or transport applications. They also have lower weight limitations compared to batteries. And also depending on the requirement, you can also get higher energy density because of the hydrogen fuel that is involved in the system, as well as better power densities compared to a number of other counterparts. So in this particular lecture, I'll be talking about specifically about proton exchange membrane fuel cells. There are a variety of other types of fuel cells which operate at different operating temperatures. So proton exchange membranes usually operate at below 100 degrees, but there are other fuel cell categories and going all the way up to 1000 degrees Celsius, which are suitable for diverse applications. These fuel cells are usually named or categorized based on the type of electrolyte or the membrane that they use. And that's where the name PMFC comes from as well. PMFCs use pure hydrogen as their fuel. Some of the other systems, other types of fuel cells can use other hydrogen sources as their fuels. Alcohol-based fuel cells, for example, can use methanol or ethanol. There are also ammonia-based fuel cells being developed now, which are not listed here. And then the high-temperature fuel cells, such as MCFCs and solid oxide fuel cells, they can operate using a variety of other gases, including methane and syngas, and a variety of hydrogen-based sources, basically. Most of the fuel cells, they provide efficiency in the range of 35 to 60% efficiency. And the efficiencies are to some extent limited by the different components that are involved in the fuel cell system, which we'll talk about later. So in the current situation, as I mentioned before, fuel cells are often put against other technologies and compared with them. And one of the main applications that is being discussed widely across the world is that of hydrogen fuel cells in vehicles. Battery operated vehicles are already there, available in the market and commercially available across the world. Fuel cell operated systems are still lagging behind in that respect. However, hydrogen fuel cell systems, they do offer certain advantages, and specifically fast refueling times, which is one of the better listed advantages compared to the other or more well-known advantages compared to other advantages. When you compare it to battery vehicles, which require hours of charging and mostly recommending overnight charging for usage during the day. Fuel cells also have higher energy density because of the hydrogen fuel being involved. And there is also a broad range of operational temperature that can be used. They can be used at sub-zero temperatures as well. In general, there is also some sort of categorization that has been assumed that battery vehicles or battery operated vehicles are dominant in the small vehicle transportation sector, whereas the fuel cells would be more appropriate for heavy vehicles. How much this is true is debatable. But as we move forward, there is good opportunities for both battery and fuel cell systems to come together for performing or developing better transportation systems as well. That said, there are still certain drawbacks and limitations of hydrogen fuel cells, which are responsible for them not being able to make to the mainstream at the kind of rate that we would like them to. This includes infrastructure requirements. They are heavily dependent on the refueling stations, hydrogen storage and transport distribution networks, unlike battery electric vehicles, which require charging points and are can be built on the existing electrical infrastructure available. Fuel cells offer efficiency of 60%, which is there is scope for improvement there. There is also a cost and durability issues associated with the stack and the individual components. All of these will need to be have been worked on tremendously in the past few decades, but they need more further work before these technologies can make it to the common man. In addition to all this, there is also a lot of ambition around the fuel cell targets for the future, reaching up to 2030 and 2040, both from the European government and also from other governments internationally, including the Japanese government, where there is an expectation of increasing the power densities up to 9.3 kilowatt per liter by 2040 and 2024 in case of EU. And these are quite ambitious targets. And to achieve these novel approaches are required for the development of the components that go into fuel cell stacks. Extensive amount of research has gone into fuel cell catalyst development, which is one of the main cost drivers for the fuel cell systems. But there are other components as well that require a significant effort going into improvising their performance and degradation so that the overall system efficiency can be improved. So within the fuel cell components, as I mentioned briefly in the previous slides with the video, there are a number of components that go into a single cell. A stack is made of a number of single cells depending on the size and the power requirements. And each cell then has a lot of different components associated with it. Primarily, there is the membrane, which is at the heart of the single cell at the very center, and that separates the anode and the cathode electrodes. There is also gas diffusion layers and then bipolar plates at the end. Each have their own distinct roles to play, and none can, the fuel cell cannot function without each one of them missing. There are specific dimensional requirements as well that are expected. The more thinner the overall fuel cell system, the more you can stack together, and the size and weight considerations are important when you're developing huge stacks for large-scale energy or power generation setups. So within the whole setup, membrane electrode assembly, which is comprised of the anode, the cathode, the polymer electrolyte membrane, as well as the gas diffusion layers, together is referred to as membrane electrode assembly. And this is a crucial or the critical assembly component of the fuel cell, without which the system will not work. This is the basic setup of a single cell if you want to generate electricity. Now, each of these components has some cost associated with it. And there is a whole range of cost variations that have been studied. Catalyst, which is primarily consisting of platinum-based or PGM-based catalysts, and it's traditionally been the case for as long as fuel cell systems have been under research. It is the most expensive component of the system. After that, the gas diffusion, the bipolar plate, is also a major component, the second most expensive component of the system, and is also adding a lot of weight to the system, because it's the only metallic or a bulky component in the system. The other components also add to the costs, and there is a scope for cost reduction at each of these catalysts, if they are each of these components, as they are improvised further for the next generation systems. So I'll be talking about individual components and what their functional requirements are within the fuel cell. So starting with the polymer electrolyte membrane fuel cells, they, as I said, they are the heart of the system. They separate the anode and the cathode, and that is how you manage to get the two half-cell reactions of oxygen reduction and hydrogen oxidation. The main purpose of the PEM is to conduct the protons and be impermeable to gases, so that the two compartments and the two half cells can function properly. So it needs to be a semi-permeable membrane, and it is designed to conduct protons, and it also has to be mechanically, chemically, and thermally very stable under the fuel cell conditions. And that is one of the main challenges that is faced by not just the PEM membrane, but a lot of the other components as well. The stability, because of the complex conditions inside the fuel cell, leads to degradation of each of the components at various rates. The most common membrane is an Nafion membrane that is used in membrane electrode assemblies used in commercial systems as well. But there are a variety of different types of membrane materials that have been studied, investigated, and are continuing to be explored within the research remit internationally. Nafion belongs to a classification of membranes which is known as PFSA, or perfluorinated sulfonic acid membranes. And this is by far the most stable and commercially viable membrane. Within the PEM, there are, as I said, the main function is to conduct protons, and how these protons are conducted or are managed to make their way through from the anode side to the cathode side is defined by or explained through a number of mechanisms. The two main mechanisms that are used to explain the possible ways of proton conduction through the membranes is the vehicular mechanism or the diffusion mechanism, and the other is the proton hopping mechanism or the Grott's mechanism. And the easy way to understand these is by looking at this figure here. The top one is defining the vehicular mechanism. For those who are not very familiar with all the chemistry, the easy way to understand is with vehicular mechanism, each proton is carried by a single molecule through the membrane to the other side, whereas in case of the hopping mechanism, the proton gets transferred from one molecule to the other within the membrane. And the membranes are doing this transport through the presence of hydronium ions, which are formed from the adsorption of water molecules that are present in the membrane. So water retention plays a key role in the transport mechanism and in the performance of the proton transport properties of the membrane itself. The PFSA membranes, they have a hydrophilic hydrophobic combination sort of structure. They have a hydrophobic PTFE membrane, and then the sulfonic acid groups, they add the hydrophilic aspect, and that allows for water retention and absorption of water molecules, ensuring that the membrane is hydrated for the proton transfer to take place. So in general, the membranes are chemically stable to quite an extent. The presence of hydrogen or oxygen does not cause any degradation of the membrane on its own in the absence of any catalyst material. The catalyst presence alone does not also cause a very significant amount of degradation to the membrane. But there's oxygen adsorption in the form of electrochemically generated platinum oxygen atoms that form bonds with platinum that can lead to membrane degradation when hydrogen is present. So there is a combination of platinum, hydrogen, oxygen gases being present that can lead to degradation of the membrane. There are hydroxyl radicals that are generated, which are intermediate species that are formed during oxygen reduction or partial reduction of oxygen. And they can attack the membrane's fluorinated end groups that leads to the initiation of degradation and can lead to further degradation or continuing degradation, especially if there is loss of catalysts, and there are a variety of other reasons there. But gas crossover can be a critical juncture for the start of membrane degradation. So within the structure, because membrane is right at the center, the membrane is compressed in between multiple layers. There is also the scope of physical degradation apart from the chemical degradation that can happen. Because of the compressive forces, there are also temperature changes depending on the cell performance, the start-stop cycles, the relative humidity changes within the fuel cell, depending again on the operation of the system. All of these over time can lead to physical degradation of the membrane. So the factors that are responsible for the chemical degradation that can lead to enhanced chemical degradation is factors like membrane thickness. Thinner membranes are generally preferred for fuel cell setups because they allow for higher efficiency and reduce losses in terms of ionic resistance. And they're also low cost because of a less amount of material being used. But that also compromises with the ability of the membrane to be permeable to gases or impermeable to gases, which means there is more chances of gassing permeating through. And as I mentioned, membrane contamination, which can happen through catalyst diffusion, platinum catalyst, loss of catalyst from the catalyst layer can lead to catalyst particles reaching the membrane and then reacting with the peroxide molecules for formation of radical ions and then initiating further degradation. And it can lead to the unzipping or the depolarization of the entire membrane polymer chain. And once that starts, that leads to the emission of fluoride ions that further lead to degradation or accelerate the degradation process by participating in follow-on reactions. And that leads to thinning of membrane and pinhole formation, which can lead to then significant gas transfer or gas crossover across the two catalysts that eventually will lead to cell failure. The other important component is, of course, the electrocatalysts. And you can't talk about electrocatalysts without talking about the support materials. Traditionally, platinum has been the common catalyst. The catalysts are present both at the anode and the cathode to assist the reactions on both the electrodes. And the reactions usually happen at the triple phase boundaries, which is at the catalytic site near the gas, where gas is available, as well as in the presence of electrolytes. So all the three need to be together for the reactions to take place. Historically, bulk platinum was used, but obviously a lot of platinum means higher cost. So the costs have been reduced over the many decades by using nanostructured particles, and nanotechnology has played a significant role in the development of fuel cells to where they are today. But over several decades, the platinum remains the most efficient or effective catalyst so far. It has a very high activity for oxygen reduction and high selectivity as well. And it's resistant to poisoning to quite an extent. And it's also thermodynamically stable at low pH values, which makes it better compared to a lot of other potential catalysts. However, there are always caveats. Within the fuel cell system, the complex conditions means that platinum is not completely it is still susceptible to corrosion within the fuel cell system. And low pH conditions in the presence of acids and the reactant gases can lead to potential degradation of the platinum nanoparticles or the bulk platinum for that matter. At specific potentials, adsorbed water on the platinum then leads to formation of chemically bonded oxygen on the sites, and these add atoms form quasi 3D lattices that can then affect or restrict the ability of the catalyst to catalyze because they're blocking the catalytic sites. Other factors that are responsible within this is a combination of the potential at which the cell might be operating, the presence of the electrolyte, the pH changes, the temperature, which again is variable depending on the operation, and also the crystallographic orientation of the platinum nanoparticles themselves. Which has led to several studies on the type of type, shape, morphology, sizes of nanostructured platinum nanoparticles. And there's more than 3 decades of work going in that, which I possibly cannot summarize within a short presentation like this, but there are tremendous options have been explored with platinum and with non-PGM catalytic materials to explore different morphologies as well as different support systems, carbon-based supports and nanostructured carbon materials for supporting of metal nanoparticles. As well as metals like tungsten that have their distinct advantages. Even within this sort of a system, carbon-based supports are then susceptible to corrosion. They bring their own challenges with them. But the use of nanostructured catalytic metallic catalyst means that the cost is significantly reduced, and carbon nano supports can be tailored to improve further. Nanostructured carbons appear or tend to offer better tolerance towards corrosion compared to bulk carbon or mesoporous carbons to some extent. And that's still ongoing work in the international community. The next component I'd like to talk about is the gas diffusion layer. The gas diffusion layer itself acts as a bridge between the catalyst and the bipolar plates. It's the gas diffusion layer on which the catalyst layer sits, whether it's developed through painting or spraying or different systems. The gas diffusion layer also provides reactant transport, and it's responsible for the liquid water, handling of the liquid water that's generated in the reaction process. It's responsible for preventing flooding under humidifying conditions. And it also is responsible for ensuring that the membrane stays hydrated when it is in the subsaturated conditions. It also needs to be conducting to collect electrons and transport them further. And it has to share the stack compression load as well. So there are different types of gas diffusion materials. They can be made of woven cloth, paper, or felt, which are non-woven. All of these are basically made from carbon fibers that are being developed using different methods and transformed into gas diffusion layers. Mild oxidation is used often to convert them to lower molecular weights, and they're further heat treated and then graphitized in some cases to ensure better stability and of the fiber. These materials are also then impregnated with phenolic resins, which act as binders to the carbon fiber networks to hold on to the structure. So the gas diffusion layer is mostly a bilayer structure. It can be a bi or trilayer structure depending on the type. Most of them is, as I mentioned, is graphite fiber substrate, but there is the bilayer consists of a fluoropolymer, which is on the surface facing the catalyst, and this is usually a hydrophobic layer, and that allows for the interaction with the catalyst, and also prevents the rest of the bipolar layer from getting wet. So ensuring the hydrophobicity, blocking the flow of excess water onto the other side. So the microporous layer usually is just a dispersion of carbon black and fluoropolymers. It's obviously a composite in nature, and it, as I mentioned, it acts as a transitional layer. It creates that heterogeneous surface chemistry between the hydrophobic and hydrophilic domains of the two sides of the gas diffusion layer. And that distinction of pores, it allows for also the carbon support particles for the catalyst layers to sit in between. Gas diffusion layers again are can also face corrosion, just like previous discussed membrane materials and catalyst support materials. Carbon materials are susceptible to corrosion. And so gas diffusion layers are also susceptible to a variety of challenges, which includes mass transport, over potential loss of hydrophobicity because of the loss of the microporous layer, and carbon corrosion on the side, which we already talked about, which can depend on, again, the presence of various chemicals, pH conditions, temperature conditions that are formed during the operation of the fuel cell. The type of start-stop cycles, the fuel starvation conditions, all can lead to a lot of carbon corrosion at the anode, and that can further lead to corrosion in the gas diffusion layer as well. The other component, or the next component after all these, is the bipolar plate. And there's a variety of different types of bipolar plates and different materials that are used. The main function of the bipolar plate is to separate the gases between single cells, gases, and allow for channels for movement of the water that needs to exit the cell. It also is a current collector for the current that's produced through the electrochemical reactions, and it electrically connects the single cells in the stack with each other. So its purpose is to ensure that there is uniform distribution of the reactants, the reactant gases that are supplied into the anode and as well as the cathode. And it also provides a solid structure to the whole stack. Heat and water management is also part of the responsibilities. So it's another important component of the fuel cell system. So given all those functions, it needs to be impermeable to hydrogen and oxygen to ensure gas losses and emergency conditions, of course. It also has to be electrically conductive. And there needs to be a balance between the conductivity and its strength. It has to have some sort of a flexibility as well, some flexural strength, and the size and weight are also important, so that because that is what is adding the bulk to the cell. It also needs to be resistant to corrosion, because we can see that corrosion is something that can happen, or degradation because of the different fuel cell conditions present. And it needs to be cheap and easy to manufacture, of course. The images that you see are one of some of the very common flow field plates, or bipolar plates. And these are made of graphite. They're usually made from a variety of different materials, graphite being the most common and traditionally being used for this. It's corrosion resistant to quite an extent. It is electrically conductive. But it has the disadvantage of being brittle and porous, and it also has high cost. So a lot of the times it's the carbon composite materials that are used instead of graphite nowadays, but they still require machining, and that machining of individual plates is quite costly. Metallic bipolar plates, usually aluminum and titanium based, are used. That does help to some extent, but these allow for the bipolar plates to be quite thin compared to the graphite plates, which are bulky. But they also require resistant to corrosion. They require some coatings, and that also applies to metallic stainless steel plates, which are also explored quite extensively, bringing their own advantages. They're lighter and thinner, and they also offer higher conductivities compared to graphite. So, depending on the applications, some applications still prefer carbon composite, carbon-based bipolar plates, whereas metallic plates are more preferred for automotive applications, given specific conditional requirements and their tolerance to corrosion. Composite bipolar plates can be used for conditions that require long life operation. These are just some images showing the degradation in bipolar plates and what that looks like before and after operations. This is obviously a very bad case of corrosion. You can also see some corrosion in the channels in the stainless steel plates. They are not as bad as the other ones, but this is just to show that they are all susceptible to different types of corrosions. There is pitting as well as grooves that get corroded, and that can lead to that can exaggerate or expand further after continuous operations, leading to further problems, because once metallic bipolar plates start corroding, they will release metallic ions, and that can lead to further catalytic activity or reactions within the cell to damage other components. So there is a definite need for protective coatings for bipolar plates, and that has been studied for more than a decade now. Protective coatings of different materials have been explored. These include metallic coatings as well as polymeric coatings. Metallic coatings, of course, have the advantage of mechanical stability to quite an extent, but they can be costly. There is the scope of having thin nano-layered coatings, depending on the method that can be used for coating development. Polymer coatings, polyaniline and polypyrrole, are quite common. They are not as conductive as the metallic coatings, and therefore there is also the need for improving their conductivity. Composite coatings are explored in a variety of ways. Carbon epoxy composites have been commonly studied, but more recently, composite coatings involving polymers and well as metal nanoparticles have been explored, and so they bring the benefit of the polymers as well as the metals with them. This is just showing some of the work that we've done in the past, looking at titanium nitride and polyaniline based coatings, as well as gold nanoparticles with polyaniline coatings on stainless steel bipolar plates. You can see the graph here shows the interfacial contact resistance that has decreased dramatically with the coatings, and also looks at the corrosion potential, which has shifted tremendously with the addition of the protective coating as compared to just polyaniline coating. The conductivity is higher as well. This is just another photograph of the actual coating. This was part of the project that we did with as part of the European Union FCA-JU project with 5 other industry partners. So moving on, we've discussed about the different components that feed into the hydrogen fuel PMFC system. And all of these have their own specific requirements. Bipolar plates in specific are an important component because of the bulk that they add and the weight that they add. And it has been speculated in literature that for further improvements in stack power density, there is contribution required from bipolar plates as well for achieving higher power density through innovation in the bipolar plate structures. For example, the Toyota Mirai, which is a commercially available car running on hydrogen fuel cells or PMFC systems, has seen significant modifications in their bipolar plate dimension structures. Moving on into the future, there's a variety of different approaches apart from just the different types of flow field channels. There's also meshes and hybrid structures that are being explored to enhance the performance of the bipolar plates. So if you try to put all the components and their losses and their requirements together, you can understand why a typical polarization curve has a number of losses. There is kinetic and ohmic losses and mass transport limitations or losses that are happening through a typical polarization curve in a PMFC, which are inherent in the system. This basically is coming from the not only the sluggish reactions at the cathode side, which slow down slow down a lot of the kinetics responsible, but there is also a lot of losses that are coming from the components, from the interfaces between the components that lead to additive losses to the overall stack performance. And to therefore improve further the PMFC performance for the next generation systems, a significant amount of work needs to be investigated for individual components, as well as looking at revisiting the component requirements of the fuel cell system as a whole, of the stack as a whole. So moving forward, there's definitely need for a lot of innovation in electrocatalysts, but they cannot completely bring down the costs on their own, irrespective of how cheap we can make the electrocatalyst. Even if we go down to non-PGM, we still need to do some sort of improvisation of the other components involved in the system. There is need for looking at integrated components or hybrid components so that there are less number of interfaces. If there are less number of interfaces and less number of components, the consequent losses, the additive losses, will automatically be reduced, and therefore the overall efficiency can be improved for the system. From the membrane perspective, PFSAs are the most common, but these are not biodegradable. There's also scope for developing different composite membranes. There is, of course, that has been a lot of work that has gone into that so far. There's also scope for developing multi-layered membranes that can have multiple functionalities, and also investigate the scope of recyclable or biodegradable membranes to make the overall fuel cell systems more environmental friendly. We talk about fuel cell systems as green technologies, but a lot of the components that feed into the system still come from fossil fuel based synthesis methods. Excuse me. There's cerium has been considered as a radical scavenger. Cerium oxides are commonly used nowadays for even in commercial systems for ensuring the longer lifetime and performance of the membranes. These are some of the approaches that have allowed in enhancement in chemical as well as mechanical durability of the membranes for long-term performances. There's also the scope of looking at regulating the hydration inside the membrane. So there is in case of less water being available or more water being available, there is balance that can be achieved within the membrane by itself. So it can regulate the water content, and the proton conduction can be managed effectively. There's also scope for exploring how much artificial intelligence and machine learning can help in designing better components and systems. There's possibilities of rethinking the stack as a whole, and there's a lot of different components that can be combined together. Gas diffusion layers and bipolar plates are already being explored to work as a single system, which can change significantly. But the overall cell structure can also be explored. The system can be revisited in terms of what a fuel cell or PMFC should look like. And I think I will leave you on that note. There's a lot of opportunities out there to develop better systems. Thank you very much.
Thank you, Dr. Survi. It's been, are you able to hear my voice?
Yes, I can hear you.
Yeah, thank you so much. It's been enlightening, and I think many participants must have understood what the fuel cells are, because we explained it right from the basics. Now, I just wanted to encourage the participants to ask questions to Dr. Survi.
Yeah, dear participants, if you have any doubts or any questions to be asked, you please raise your hand and we will unmute you.
Okay, ma'am. I have an question. Ma'am, what will be the cost effective of the fuel cell?
What will be the
cost?
cost?
Yeah, cost effective, like compared to the like your conventional fuel like petrol and diesel. So how it can be beat the cost effectiveness like this, sir?
That is the major question, and that I think that is one of the big reasons holding the technology from being commercialized at a large scale.
Yeah.
The cost of hydrogen is itself is a concern at the moment. So if you need to run fuel cell, for example, in the automotive sector, the infrastructure and the cost of hydrogen first needs to be there. Refueling costs would be too high otherwise for the consumers. But the fuel cell system itself, there is a lot of work that has gone into reducing the cost of the catalysts, and the system cost has come down significantly in the last decade or so with reference to the catalyst costs. But as I mentioned in the lecture, there are other components that can be investigated further to reduce the costs, and bipolar plates are one of these components that can be used to achieve further cost reduction, as well as the gas diffusion layer, and combining those different components together into integrated components is one way of developing more cost-effective systems.
Yeah, thank you, ma'am. Some question came in the chat box.
Sure.
No, Jivtesh, actually Vishnu Sonavan is ready to ask a question. Vishnu,
Yeah.
you can ask.
Vishnu, please continue. You are unmuted. You can ask the question. Vishnu sir.
Maybe some internet issue. So we can take one question from chat box actually. So
There is a participant named Ravi. He's asking how safe are fuel cells for the environment?
The question is quite broad. Is there something specific you want to ask? I mean, in general, this is a green technology, and that from that perspective, it is safe for the environment. But if there is something specifically you want to ask about the fuel cells, that might help. The disposability. So I think there is, in terms of fuel cells, there's a lot of components that can be recycled. The catalyst can be extracted to good percentage. So platinum catalyst can be reused. The recyclability off the top of my head, if I remember, or the disposability from that perspective for fuel cells is slightly, or is better than the lithium based batteries. There is a lot of issues with recycling of the batteries, but the fuel cell components, because a lot of that is carbon based materials, it can be managed better. That is my understanding. And the catalysts or metallic catalysts can be extracted for reuse. Can bipolar plates be manufactured by 3D printing? I think there's a lot of work in that direction happening. It's the machining of the channels or the micro channels that can be explored interestingly with 3D printing, I think. Is it safe for tractors? Yes, it's safe for all sort of, in fact, it's preferred for all sort of heavy vehicles compared to batteries. Safety is usually what people ask about with reference to hydrogen being involved, but that's fair. That storage has been developed for safe use. So if it's safe for batteries, it's safe for the fuel cells as well. Batteries, for that matter, are more inconvenient for tractors because they add a lot of weight to the tractors. Fuel cell systems are much lighter, so they are actually better suited for tractors. In GDL, how materials like paper and cloths are integrated. That the paper or the cloth is made from carbon fibers. So it just depends how the fibers have been put together, whether they're woven or they're non-woven, and they're made into some sort of sheets. There are different methods to that, and that is a separate discussion, actually. There's a lot of different ways, and I am not involved in GDL fabrication myself, so I'm not the best person to answer. But that is the carbon fiber material that can be easily made into a mesh or a woven cloth kind of a material. What are the current research areas in the field of fuel cell? There's a whole lot of research areas. We've only talked about the components and the requirements. There's a lot of electrochemical research developing performance, increasing performance. Balance of plant is also something that needs some improvement. There is also a lot of investigation on how the fuel cell systems can be integrated into different applications, and that requires research on its own and testing. So there's a whole range of areas within fuel cells. Some insights about hydrogen storage in high entropy alloys. Hydrogen storage is something I'm still just venturing into, so I don't think I'm best suited to answer that one yet. What will be the life of fuel cell? The life of a fuel cell depends on the stack the cell operation, the application that it's used for, the start-stop cycles. There's a variety of conditions that you need to know before you can say what would be the life of a fuel cell in the given condition. It's if you think of it from a battery perspective or try to compare it with the battery, depends on where you're using the battery, which application, how it's going to be run, how often it's going to be charged or how discharged, what would the power requirements, all of that defines the battery. Similarly, there are a lot of factors that would define the total life of a fuel cell and how the components in the fuel cell actually degrade over time as well. Catalyst coating on the membrane, which is the best method? Air-driven gun spray, Dr. Blade, or brush coating? I think the spray is more commonly used in the commercial system. I'm taking a risk there, but I think there's still scope to develop better methods for catalyst coating.
I have a question, Dr. Surabhi.
Yes.
Is there any alternative for the platinum in case of catalyst?
So alternatives are continuously being explored. Commercially, that still seems to be the best. There's a lot of work that's gone into bimetallic and multimetallic catalysts using including non-metallic catalyst systems are being developed. Platinum-free systems in which are non-PGM metals are of course being explored. The nanostructured catalysts sometimes offer better advantages, and alloys can offer advantages to compared to platinum, but most commercial systems are still using platinum. So it's hard to say unless certain catalysts have been tested for long duration in the real fuel cell. It's hard to say whether it's better than platinum or not.
Yes. And one more thing, you mentioned that bipolar plates, one of this function is current collectors, but
yes,
as far as I know, current collectors are different from it's a different part from the bipolar. Is it?
So I think there are current collectors at the end of this the stack.
Yeah.
And inside the stack, you have individual fuel cells stacked together. So the bipolar plates can act as current collectors for the cells in the stack, inside the stack and then allow for current to be
Okay.
Yeah.
Right. I think we can conclude the session. I think there is one more question. Can we expect rapid changes in the utilization of fuel cell from the existing technology?
Rapid changes in the utilization of fuel cells? I'm not sure from the existing technology. I'm not quite clear on the question.
Yeah, I think it is too broad. I think.
Yes, I will. Sir, one question someone asked regarding the storage system. So on the 12th October, there will be a session on the storage system, Professor Anurag. So regarding that, we can clear about the question, everything. So it will be on 12th October, there will be a session. So for now, we can conclude the session. So sir, please, Vishwanath sir, please.
Yes, ma'am. I think thank you so much for your session.
Thank you.
We are happy to actually collaborate and make these sessions so enlivening for all the participants. Many of them are budding engineers, budding researchers. So I think it will be helpful for them, and some of them are students as well. So we thank Dr. Surabhi for her time because it is late in the evening, I understand.
It's coming up to 5:30 in the evening, not too late, but yes.
Yeah, thank you so much. Thank you very
Thank
much.
you.
Now I leave it to Anuhya ma'am to introduce our next speaker, Jun Peng, who is a Professor Jun Peng from China. Thank you so much, Surabhi. Thank you very much. We would love you to be continuing in the session. Thank you, if it's possible.
Thank you. I'll try to continue for as long as I can.
Thank you so much, ma'am. Thank you.
Thank you, ma'am. Now I take the privilege to introduce our keynote speaker, Professor Jun Peng, Professor of Sustainable Energy Engineering, School of Engineering, College of Health and Science, University of Lincoln, United Kingdom. Professor Jun Peng has received his PhD degree from National Engine Combustion Lab, current State Key Lab of Engines, Tianjin University, China, in 1996 for a research on the investigation of high-pressure fuel injection and spray characteristics. Then after 4 years working experiences as research fellow in Brunel University and 2 years as senior development engineer in Ford Motor Company, he held the position of lecturer since 2004 and senior lecturer since 2007 in the University of Sussex. Prior to his current appointment, he worked as professor in engineering in the University of Bedfordshire. Jun Peng's research interest lies in thermodynamics, fluid dynamics, and combustion with applications on flows and combustion in IC engines, gas turbines, fuel cells, and other sustainable energy systems. His research has involved both numerical simulation and experimental investigation, including various laser diagnostics. His recent research works have contributed to sustainable vehicle powertrain, non-carbon water transport technology, combination of solar PV and solar thermal for energy efficiency, improvement, etc. Jun Peng is a fellow of IMEC-E, Chartered Engineer, recognized by IMEC-E, and a member of Professional Review Committee of IMEC-E. He was an invited fellow of Japan Society for the Promotion of Science, JSPS, and the associate editor of IET Journal of Electronics Letters, SCI Indexed. Industrial collaborations are like Eminence Limited and on an innovative UK project, Siemens Engineering, on a decarbonization project, AVL, on free software licenses and collaboration projects. The audience is eager to benefit from your knowledge, sir.
Okay, I can start now.
Yes, sir. Please. We welcome you.
Okay.
Thank you. Thank you.
Okay, let me share my screen. Is my sharing okay now?
Yes,
From
Professor.
your side?
Yes, yes, Professor.
Yes.
Yes,
Okay.
sir.
Yeah. Okay, thank you so very much, the chairman, for your introduction to my background. Also, thank you very much to the head of the school, Professor Chala Pazi, and Dr. Panda for your invitation for me to join this short training course. And yeah, and say hello to all the colleagues in India and and also across all the other countries. At the moment, I think in India just past 12 o'clock, yeah, lunchtime. In UK, we are now it's 7:30. Yeah. So my my topic is the role of the carbon-free fuel. Actually, it means about hydrogen, but more or less including ammonia for the net zero. So I will include in 5 the part of my talk. First of all, is regarding net zero target and strategy. Then is carbon neutral for the transport. Yes, some of the more general information. Next part is about the battery electric vehicle and fuel cell vehicles life cycle emission analysis. And the first part is about the carbon-free fuel production and applications. Finally, give you some brief about my current research, use the carbon-free fuel for the combustion, yeah, mainly for combustion. And on this slide, you can find actually left-hand side is UNFCCC's COP26. UNFCCC is stand for United Nations Framework Convention for the Climate Change. And the COP26 is a conference of parties. 26 actually take place in November, December 2021 in Glasgow, UK. On this COP26, 137 countries actually has communicated the net zero strategy. From this slide, we can find actually like UK, currently I'm working in UK, so we set as 2050 to get zero carbon emission, or another I would like to say is greenhouse gas emission get zeros. Relevant country like India is actually 2070s, and China is in the world the biggest country for the energy supply and the consumption is the 2060s. From this information, actually, I got 6 countries. Yeah, this color, the kind of colors. They claim they have achieved net zero greenhouse gas emissions. I double checked the information. Actually, here we can find Bhutan. Yeah, Bhutan is between India and China. Actually, Bhutan is get 100%. This electricity almost get the renewable energy for the power generation. Also, Bhutan's transport, they don't use too much fossil fuel for the transport. So Bhutan seems they have achieved the net zero greenhouse gas emission. For other 5 countries like Benin, Guyana, is other 5 countries, they still use a big part of the fossil fuel for the power generation, even for other sector. So it's difficult to say other 5 countries, they have achieved net zero greenhouse gas emissions. So let's we move ahead. It's more general information regarding net zero strategy. Different country, how they can take the net zero strategy, the policy to meet the requirement for get net zero greenhouse gas emissions. Some information here. See, China, so just I mentioned, is the biggest country for energy supply and energy consumption in the world. China said it's the 2030s in 7 years, they will get to the peak of the greenhouse gas emission. Then take the 2060s, gradually from 2030 to the 2060, take 30 years from the peak point, then to get a zero greenhouse gas emissions. Another second biggest country is the USA. From this slide, we find USA also take the 2050 as a target. So by the 2060, that's USA, they got different sector, how they reduce greenhouse emissions. By 2050s, actually zero is this point roughly. Yeah, not the, here is not the, yeah, actually, here is zero, means by the 2050, greenhouse gas emission, some sector, they still got more or less some greenhouse emission. But another sector is the land use sector, because we know like agriculture side, once we got plant growing, the plant need to absorb some of the CO2 from the atmosphere. Then from land use sectors, by 2050 in USA, big amount actually is negative CO2 emission or greenhouse gas emission. Then totally by the 2050, even the USA claim you can get a negative. Yeah, we can find actually these dot lines, yeah, dashed lines, and here is a zero. So roughly you can get that some negative greenhouse gas emission. That's about USA. I take another very special country as an example. Later I give you a reason why I take the Norway as examples. Norway totally the greenhouse gas emission not very high. You got a 60 million tons annually. So Norway, they currently is not very clear like on this slide here. They got this color is not clear, no target. Yeah, Norway, but Norway running very good. Norway in the world is cleanest the country for the power generation. Yeah, they use the most 97% hydropower for the power generation. So Norway 2022, the older 85% new car actually is battery electric car. So Norway, they can run even by the 2030s, they can almost get net zero greenhouse gas emission. Or if they get the work probably take a little longer, they can probably at least 2050. I like come back to this slide. That's Norway currently power generation, the consumption. Almost 90, we can find almost 99 from this chart is use renewable or hydro power for the power generation in Norway. How about the UK's case? Actually, is I working in UK, give more, I can get more probably information, more data of the UK's case. The UK currently running from the UK take the 1990s as a baseline. Then they start working for the reduced greenhouse gas emission. In the 1990s, UK got 800 million tons per year, the CO2 emission or greenhouse gas emission or CO2 equivalence emissions. Running by the pandemic 2020s, we're close to the 400 million tons CO2 equivalents greenhouse gas emission. So UK in these 30 years roughly reduced half of the greenhouse gas emission. Then just from the first slide we have mentioned, the UK targeted by the 2050 to get net zero. So it means from 2020s get another 30 years. UK with the current, past 30 years, they with this same trend they can meet the net zero, the target by the 2050. That's UK. How they make this? That's in last 30 years before the 2020s. The mean reduction of the greenhouse gas emission in UK actually is the energy supply sectors. We can find like here, the energy, the CO2 emission at the point 200, probably 70 or 80 million tons per year, reduced to the less than 100. These are energy sectors. And like West processing sector or more than some reduction, and the other sector, residential sector, business, all they got more or less some reduction. One very special the sector is the transport. We can find that in last, before the 2020s, in last 30 years, roughly almost no reduction. So the R&D people working in transport sectors, they're working very hard to improve the efficiency of the, like the passenger car, like the tractor, improve the energy efficiency to reduce fuel consumption. But why the transport sector CO2 the emission almost no reduction in past 30 years before 2020s? Because the volume, the amount increase a lot. Or the car the size, more powerful, more bigger engine, so makes even the efficiency increase a lot. But the car engine still use, for example, use a petrol car, diesel car, still use the same amount of fuel. That's why in the transport sectors, past 30 years before the 2020s, in transport sector, almost no reduction in CO2 emissions. So in next 30 years, later we give you information. UK, also got a target for how to reduce the combustion engine transport, then gradually convert to the battery electric transport, then gradually we can get a net zero. So that's plan in next 30 years, from roughly from here, for example, the UK's plan how to get the by the 2050s. UK currently actually running the every 5 years get the plan for the credit, for the carbon emission credit, then get review. Is this 5 years met or not? Is only other point need to get some probably some optimization for reduce greenhouse gas emission. That's UK is running this. In 2021, October, UK government, Boris Johnson, probably, his government published this UK net zero strategy, totally 361 pages. In these net zeros, more like white papers, they give almost all the detail. For example, technology side, how to make in next 30 years, how to less this 400 million tons CO2 get reductions. For the financial side, how to get the government investment to different sectors to improve the probably engineering, improve some product production, improve technology to reduce the greenhouse gas emissions. That's in this net zero strategy, UK net zero strategy, that these white papers, by the 2050s, how UK get the energy supply and energy consumption. the government plans. Roughly half by the 2050s, and the UK, the energy supply is definitely renewable energy, green renewable energy, like the wind, big part. Currently, UK roughly 15% energy supplied by wind energy. By the 2050, probably around the 2030s, is wind energy. Another is currently government also put a lot of money for developing the next generation of the nuclear power generations. That's another part, and also solar energy. This kind of the part actually provide electricity to running transport, like the battery electric vehicles, like building electricity, like industry for different use. Another more or less electricity go to the electrolysis is coming from here to here. Yeah, we talk about it later. And the second main part actually is about the biofuel biomass. We know currently biofuel biomass life cycle is not a net zero greenhouse gas emission, because for the like biofuel production still use a lot of the electricity. National grid electricity still use a lot of the like the biofuel, fossil fuel for the power generation, still some CO2 emission. Also tractors use diesel, yes, also some emission. So currently the biofuel biomass not net zero, but by the 2050, because all the electricity, all the tractor, all the machinery also use the net zero fuels or energy. So by the 2050, biofuel biomass also can get a net zero. So this part net zero. By the 2050, from government plan, still some the fossil fuel, like use of natural gas to get a different application, like the transport hydrogen, like the building hydrogen, yes, still, but this use the hydrogen. So how to get a net zero? Use CCS, carbon capture and storage. So use the natural gas, hydrocarbon, so with the CCS produce hydrogen. Some hydrogen from here, from renewable green energy, by the electrolysis produce hydrogens. So the hydrogen we can find in the future play a very important role in UK. Almost we can find almost half hydrogen by the 2050s used for the building hydrogen, like in the house, people use the cooking, the central heating, and the transport, like use hydrogen. Just Dr. Sharma give introduction about use the fuel cell to running the transport. Another industry also is a transporter for energy supply, energy consumptions. And also hydrogen, some hydrogen going to the thermal power generation, produce electricity again. So why we need the electricity, hydrogen, and the electricity again? So later we'll give a reason why we need to run this. And the industry in the future still use some coal, like for the steel production, iron production. That's also will join with CCS, get net zero. And some fossil fuel use actually oil or lubricant, not for the reaction, not for the combustion. So for this part, fossil fuel will CO2 or greenhouse gas emission. This is just for the oil for lubricant. So that's by the 2050, how UK will running the power supply, energy supply and energy consumption. What I like to say from this slide is this. Let me go to the point here. Yeah, actually, it's this area is hydrogens. So in UK claimed in the world for the running the actually is net zero is definitely leading country. So they are got a plan for the hydrogen, use the hydrogen technology to reduce, to meet the net zero. So we can from this slide to see in India and for other countries, how we can use the hydrogens, how from the research R&D area. So like me, we do research, how we think about the hydrogen for our, in our research, provide for different new technology for the power system in the future, provide for different application. That's where we are working. This area gives some more or less some information currently in the world, how much how we can in the UK, how we can got power generation. Actually, most still fossil fuel is natural gas here, and some nuclear, some wind turbine, wind energy, and some solar energy, some probably biofuel biomass. In the future, this part need to get the CCS or totally use the wind energy to replace. That's about the world. In the world, still out of coal for the power generation, roughly 40%. We know in India, in China, still even over 60% is power use of coal for power generation. Why we need the actually hydrogen? Because the hydrogen actually for the energy storage, and because once sometime we got the winter energy like the middle night. Actually, middle night always compared to the daytime always got the most strong wind. So middle night actually from national grid we got extra electricity we can't use because the middle night industry stop a lot and the residual use energy less. Then a lot of the energy from any wind farm can't be used. Then this kind of the extra electricity can by the national grid controller can tell the hydrogen hydrogen production station to convert extra electricity to the hydrogen, then store the hydrogens. Once we need the hydrogen for different point, for example, to charge the fuel cell vehicles, we directly to use the stored hydrogen to charge the fuel cell vehicles. That's one reason why we need the hydrogen. Later, I got more information about this. That's about in the UK. In UK, currently 1 town has started work. This town's name is Low Semleys near the Newcastle. This town by the 2030, next 7 years, will all the converted house currently use the natural gas all convert to the hydrogen. Means we need to develop like the new boiler technology. This boiler to get the combustion for hydrogen rather than natural gas. Then we can get the coking, we can get the central heating. That's a way, yeah, in UK, different sector now has started working for how to develop the hydrogen technology. Then we can use hydrogen for different sector in addition of the fuel cell for the transport. There's some about background information about the net zero target and strategy. Then we learning about why hydrogen is so important in the future meet net zero strategy. Next, we give information for the transport sector, how we can get net zero by 2050s. On this slide, we know this is not very strange for us about in the future for the passenger car sectors. We can get net zero. We can use battery electric vehicles like currently in globally is 2021 near over 60 million production of the battery electric vehicle and plus probably biofuel vehicles. And last year also 2022 just in China near the 6 million, near 6 million battery electric productions. So this keep a big increase. In the future means in the passenger car sectors, we have no worry. If we can make electricity, definitely it's clean electricity all the countries. So for the battery electric truck itself, no worry, all the battery electric car, actually it's kind of like Tesla car, we can get the car on board get net zero. If we got electricity net zero, so life cycle, we can get a net zero greenhouse gas emission for the passenger car. So fuel cell vehicles, just Dr. Sharma has given information. This will more or less give you the port on the battery electric car. In the future, definitely some percentage passenger car will run by the fuel cell. Actually, now has got like in USA, like in Japan, some 100,000 fuel cell car has got running. In UK, only some 100. UK only got 13, 14 hydrogen production station or hydrogen refueling station for passenger cars. Also, Tesla recently has tested their battery electric truck, and we have probably learned this kind of information news. In the future, tractor, commercial heavy-duty vehicles also gradually will powered by the battery electric vehicle or fuel cell vehicle. So if we go to the hydrogen and the electricity production get net zero, means in the future, road transport will be get net zero. That's technology side. And the UK actually just last week and before last week, UK's plan by 2030s will stop all the new car powered by the combustion engines. And now the government just changed the plan last week, not government, from the conservative with the parties. They are control in UK control the government. They change the plan now more than 2035. All the new sales car need to get rid of the combustion engine, or means by the 2035, all the new car need powered by battery or hydrogen fuel cells. Another information in Norway is 2025, all the new car must be powered by the non-combustion engine vehicles. And 2022 in Norway is 85% of the new car is battery electric vehicles. So they're running very good for Norway. So means no problem by 2025. They can meet the plans. Rail transport, we know currently electric trains technology has been there, got very much the development. In China, we know a lot of the fast train. Now it's almost probably we can say 80–90% train, passenger trains powered by electricity. In UK got HSP has the train plan from London to Birmingham, and actually then to the Manchester just last week. Also, government changed plans. They stopped the plan from Birmingham to Manchester. From London to Birmingham, still this electric high-speed train. In UK, most train now running by electricity. Even still some passenger train running by the diesel engines. So means by the 2050, all the train need running by electricity in UK. If UK need to meet the net zero target. For the air transport, how we can get the technology to make the net zero? This one example. Company name is Aviation. Aviation company test this all electric aircraft. They got to test this prototype in September last year. These are American companies. This 9-seat passenger aircraft totally powered by batteries. So totally the aircraft just over 8 tons, but the 3.5 tons is battery. So they carry this 9-seat aircraft can running 650 miles. And with two electric motor, and each is 640 kilowatt. So that means this propeller not powered by jet engine, it's powered by electric motor. So this electricity aircraft, this one technology can running if we don't care too much about the range, because this range only covers 650. For bigger one, like some like A380, if we're running some over 10,000, around 10,000 miles, or with 800 passengers, how we can get a battery to support the bigger commercial passenger aircraft. This is another issue in the gradual get development. And another company named Zero RVL, they got a test in January this year, tested in UK. They test this side propeller also running by electric motor, but not directed by battery. It's by the hydrogen fuel cell technology. So means this aircraft takes hydrogen as fuel to running the fuel cell produce electricity. They running the high-speed electric motor power the propellers. That's also got access test. This aircraft is a 19-seat aircraft, passenger aircraft. So it's one option is the battery, another fuel cell for the aircraft. This test, I remember they didn't give exactly information how long, how about the range for the test. So we got more information about the air transport. This published is 2020 September. Airbus published the news, and they got plans by the 2035, another 12 years. Airbus will running their new commercial passenger, very big passenger aircraft by hydrogen jet engine, not the fuel cells. So as one main supplier of the Airbus jet engine, this Rolls-Royce has running the test in last November is November 2022. They have test jet engine with hydrogen as fuel. They have made the test. They got running wells. They make a successful test use hydrogen as fuel rather than the currency as fuel. So in the future, we can find for the commercial passenger aircraft, we can run by battery, we can run by hydrogen fuel cell, or we can run by hydrogen jet engine, big jet engine, more powerful one, to running big commercial aircraft. So that means by the once over globally, we make a net zero from air transport sector, we can running different net zero technology, battery or fuel cell or hydrogen jet engines. We got different options to running air transport. So we talk about so far ground transport for passenger car, for the tractor, for the truck or lorries, or air transport, rail transport. How about the water transport? For the water transport, because there's a more heavy commercial, the engine will be used. Technology little bit slower than other sectors, but from the 2021 IMO, International Maritime Organizations, the symposium, they published this kind of information. By the 2050s, if globally we made the net zeros, roughly half the power or energy running the running the water transport or bigger vessel or bigger ships will be used the hydrogen or ammonia, 45%. Or some more or less when the proportion, some battery, left half is running by the petroleum base or LNG or hydrocarbon base or methane or other fuel, the hydrocarbon based on the fuel, the engines. So if we need to get net zero, means for this part, this half roughly hydrocarbon fuel power the big vessel or small boat will be get the CCS, then we can get the net zero. So means in this area need some technology development to reduce to capture CO2 and storage CO2. So here give you more or less now you can find we are not just talking about the hydrogen. Also we need including ammonia top of the carbon-free fuel. Why? Later we give reasons. So there's some examples in the world. Yeah, different prototype. Yeah, different prototype. The water transport running the big boat, small boat, big vessels, or big internal combustion engine for the maritime applications. So there's a man they have got the running the developed some ammonia fueled the engines running like find this examples running ammonia. So ammonia actually is some kind of similar as hydrogen, some kind of the carbon-free fuels. Another company, Maersk, they have a claim they got in the world running first one container vessel with the methanol as fuel. Here we got some information. Some company also this big project that's this human-made the methanol use actually hydrogen from renewable energy to produce hydrogen by the water electrolysis. Then use the hydrogen collect CO2 from power generation stations, join together produce the methanol. So they claim they got they can take knowledge produce the CO2, but CO2 not from fossil fuel, CO2 from the not directly from the fossil fuel. It's from they collect the CO2 from power generation station. So that's they still said at least from the big vessel fuel supply to finally got emission. This cycle they got zero CO2 emissions. So for running this kind of bigger engine, actually need some special engine combustion technology. Yeah, because it's not a diesel, it's the methanol or hydrogen or ammonia need a special technology like this kind of. They use actually deal the fuel injectors to use more or less some the diesel fuel as the use the diesel fuel to ignite the methanol, some technology. This is not more talk about the hydrogen. We don't get too much about that. Next, I'd like to give some information. It's my group. We did some analysis how about the life cycle, the emissions for the battery electric vehicle and the fuel cell vehicle. Then get a comparison. How about the life cycle CO2 reduction? Yeah, currently or in the futures. Yeah, we got this kind of information. Life cycle is talk about from the vehicle side, from vehicle production. How much CO2 it release. Like here we got information. Yeah, like standard gasoline vehicles, average produce one vehicle roughly release 5.6 tons CO2 equivalent CO2 greenhouse gas emissions. Battery electric vehicle is 8.8 tons. We can find the battery electric vehicle production produces more CO2 than gasoline engine vehicle because battery production consumes more energy. It's not a charging, it's a production stage. So that's a hybrid is between the 5.5 and 8.8. That's for the vehicle production stage, some CO2 production current technology. And the vehicle recycle final stage also release some CO2. Vehicle operation, maintenance, consume the fuel, release more CO2. So like the internal combustion engine vehicles, we got the fossil fuel produce gasoline or petrol fuel or diesel fuel, and running diesel fuel on the vehicle produce CO2. Produce petrol fuel or diesel fuel also release some CO2 at the fuel production stations. Currently in I don't know how about in India, in UK, in Europe, in China, all the passenger car, the fuel, petrol fuel got or diesel fuel also got more or less some the biofuel. In UK, 10% the petrol fuel got the bioethanol, 7% biodiesel in diesel fuels. That's currently. So we including from the fuel production and the field operation in a vehicle production, vehicle recycle, all put together, one vehicle, how much CO2 we got a life cycle analysis, life cycle CO2. That's what we are doing for the internal combustion engine vehicle. For the battery electric vehicles, this area is similar, only is battery electric vehicle production stage higher than petrol engine vehicles. More CO2. But for the battery electric vehicle, for the electricity productions, so this is more country that talk about the life cycle CO2 because electricity, different country got a different electricity production. Like in UK, natural gas, wind energy, nuclear energy, hydro power, solar energy, all we should include. And like wind energy, probably we say wind energy is zero CO2. Actually, if we talk about the life cycle, it's not zero CO2 because from the wind turbine production also release some CO2. Wind turbine maintenance also release some CO2. Wind turbine final recycle also release some CO2. So we talk about every power generation sectors. Also, we think about for this sector how much CO2. And another case, just I mentioned about the fuel cell vehicles. From power vehicle production, this apart from this, where we got the hydrogens, we can use the hydrogen, for example, from the national grid, got electricity, water electrolysis, produce the hydrogen, or we can like just in the beginning we mentioned, if the national grid controller, the controller find we got extra wind energy, wind electricity, we can just use wind electricity, wind energy to produce electricity to electrolysis produce the hydrogen. So we can get a very low CO2 emission of hydrogen. Or currently in the world, most hydrogen actually produced by the natural gas refarming. Fossil fuel by refining produced hydrogen. This got more actually CO2 emission currently if no CO2, no CCS, no carbon-carbon and storage. So we consider the hydrogen from different hydrogen production, then we joined all together. We got a life cycle CO2 emission from fuel cell vehicles. Then we can compare between the internal combustion engines vehicles to the battery electric vehicles to the fuel cell vehicles, how about the life cycle greenhouse gas emission. So we take internal combustion engine vehicle, take this 4 passenger car model as for the internal combustion engine vehicles. So we give information, how about the power, how about the fuel tank, how about the range. And we take this 6 for the battery vehicle as the examples for our life cycle analysis. So like the Tesla car, like a BMW i3 cars, that's the power. That's more powerful compared to the internal combustion engine. We can find more powerful. That's a fuel tank. That's range. We can find that internal combustion engine always got a longer range than battery electric vehicles, then lower power than battery electric vehicles. On the other side, we take these 4 production vehicle, fuel cell vehicles, just we mentioned like 3 actually is Toyota Mera, Honda Clivic, and Honda iX35. So the power is between internal combustion engine vehicle and electric vehicle, battery electric vehicle. Range is is actually is higher than range is higher than battery electric vehicle, but lower than internal combustion engine vehicle. So we can compare these 3 different type of vehicles. Range and the power is very different. Some would like a battery electric vehicle say, oh, I got very powerful, but you got to lower the range. Internal combustion engine vehicle can say, oh, I got a very long range, but you got lower power. How do we compare? We got these definitions. We consider power and range together. We got this parameter SRPR, square root, power and range. Then we can compare 3 different vehicles. There's a battery electric vehicles, energy consumption rate per kilometer, how much megajoule. That's the internal combustion engine vehicle, that's a fuel cell vehicle. We can find that fuel cell vehicle consume more energy than the internal combustion engine vehicle compared than battery electric vehicles. Then we consider different the countries. That's UK. UK how to produce electricity. More energy from natural gas and some from the. How I can stop here? Actually, okay. Come UK. So this I think is biofuel biomass. Or this bio, this nuclear, this hydro, this wind. UK. This is 2019 published from IEA, International Energy Agency. This is China. They published by EA. This is published by China. China is over 60% power electricity from coal. India similar. Norway, we have Norway most electricity from hydropower. So different power generations. Get a different CO2 emissions or greenhouse gas emission. So from the national grid, different country you can find. Norway got a very low CO2 emission from the electricity. UK 300 some, China 600 some, India 700 some, because power generation from different energy supply. So we consider different energy consumption rate for different vehicles. Then we finally, in Norway, you can find and always battery electric vehicle got a lower CO2 emissions than internal combustion engine vehicle. UK is, if we're from here, think about this bigger and bigger vehicles. UK similar, internal combustion engine vehicle and battery vehicle similar. And China is battery vehicles even higher CO2 emission in internal combustion engine vehicle, because in China, electricity not clean enough. Use the coal for power generation produce more CO2 emissions. Fuel cell vehicles, we consider different case. First one is the blue one. Blue is use wind energy produce hydrogens. We can find out fuel cell vehicle can get very low the CO2 emissions, life cycles. All countries similar. Another is green one for the actually also similar 200. Green one is from natural gas refarming produce hydrogens. Currently in the world, over half hydrogen is still from natural gas refarming. So the yellow one from national grid electricity by the water electrolysis from hydrogen. We can find different countries were different. So in Norway, we can get the fuel cell vehicle kind of get very low CO2. UK, yeah, it's not good, not advantage fuel cell vehicles. China even were high from fuel cell vehicle, got CO2, much higher CO2. So in China means running by the national grid electricity, produce hydrogen, running a fuel cell vehicle is not worse for reduce CO2 emission. That's our life cycle analysis side. Why we need hydrogen? Just we mentioned, national grid from wind generation. If we got extra energy, we can't store to somewhere. Difficult to store. We need to find some technology to store. Other words, supply side to the consumption side is not balanced. National grid always need a balance. Consumption side or supply side. If we got extra electricity, means need to store some energy. If wind energy, extra wind energy, need probably to dispose some of the wind electricity. Or if the supply side is not enough, means somewhere we need to stop some power consumption. That's why in different countries, still sometimes the power, the residential house or some industry, not always can get the electricity. So why we need hydrogen for the energy storage? Because the hydrogen storage can power and store time can get a very good the advantage compared to other technology. How other like a supercapacitor, like a battery, where's battery got very good battery somewhere. Yeah, probably now battery is here. And that's for the power and the work, because we know battery too expensive. Battery got very good efficiency. Like here, battery got a very good efficiency. Supercapacitor also got very good efficiency. Hydrogen energy efficiency is very low. But if so low hydrogen efficiency, why we use hydrogen? Is the cost side, capital investment. We know battery more expensive. Hydrogen, we just need the water electrolysis and electrolysis and use the metal, the tank to store the hydrogen. So the cost side is very low. Very big scale, national levels, so the hydrogen you got somewhere go to the advantage. That's why currently UK take the hydrogen as a priority to store the energy storage. That's UK currently, I mentioned, has built 13 hydrogen production refueling station to refuel the fuel cell vehicle in the UK. They store the hydrogen here. They got a national grid electricity, national grid controller can control the hydrogen stop and start, then store the hydrogen in the high pressure tank, then refueling the fuel cell vehicles. That's about hydrogen, some property. We jump over this area. Just Dr. Sharma had mentioned about fuel cell vehicle. They give you one example. This Toyota second generation, the Maron, secondary Maron, the fuel cell vehicle. 3 yellow, the tank is for stored hydrogen. They stored 120 some liter hydrogen, can store 5 kilograms. So the hydrogen very light. That's why I need a solar of the tank. So running the fuel cell somewhere and running this battery, then running the electrical motor, running the fuel cell vehicles. One fuel cell vehicle, the second generation, now sold in UK roughly over the 50,000 pounds. Compared to Tesla Model 3, 42,000 pounds. Compared to BMW 3 Series, normally just over 40,000 pounds. So the fuel cell car little bit expensive than other technology cars. So we don't need this. Just to mention why we need ammonia at the mean ammonia advantage is can get that's for kilogram energy storage, ammonia is not advantage. So hydrogen got per kilogram hydrogen got more energy. Liquid or compressed or uncompressed hydrogen all got higher energy content than ammonia. There's a hydrogen. You can find the per kilogram got to the 120 millijoule. Ammonia, with ammonia? Ammonia only got the 18.6. There's a hydrogen. But by volume side, per liter, the million joule, that's per kilogram million joule, we can find the difference. There's ammonia. Ammonia, we can either got stored as a liquid. Ammonia with 10 bar the pressure or minus 33 degrees temperature can convert ammonia as a liquid. Hydrogen, very difficult liquid, even can get a liquid, very high pressure and very low temperature, minus 253, so we can find it very difficult. So there's liquid hydrogen, there's compressed hydrogen, there's gas hydrogen. We can find by volume, there's ammonia, the liquid hydrogen, compressed 700 bar or 70 million bar per the pressure. This unpressed hydrogen. We can find even by mass, hydrogen got an advantage than ammonia, but by volume, ammonia got an advantage than hydrogen. That's why big vessel, and also for the tractor, and also the passenger car, the size so important, volume so important. We can store more energy, use ammonia than hydrogen. That's why we need ammonia. So ammonia production, normally once we got hydrogens, from water electrolysis, joined with nitrogens, joined with nitrogen by the chemical process, we can produce ammonia. So that's ammonia production. Also from the renewable energy, we can get a carbon-free ammonia or carbon-free hydrogens. But talk about from mobility, mobility sectors and the passenger car, water transport, even the air transport, the aircraft, if we use ammonia, we can take more energy, use a smaller size, smaller volume tank. That's why ammonia. But why we don't use ammonia? We have got only example is ammonia for air transport, passenger car. Jet engine running ammonia is very, very difficult because the low ignition, high ignition temperature and low, we can find it. Ammonia, there's hydrogens. They got a lower heating value ammonia, and the flammability limit is narrow. That's about the hydrogen. Also, combustion, the ignition temperature is higher. Also, for the release, also the measurement boiling velocity is lower. That's why running ammonia more difficult. So I'll give you more or less about our group, what research we are doing. Actually, we are doing currently for ammonia combustion. We try to use the two fields for internal combustion engine for the water transport. Ammonia is a premix with air. Then we inject some hydrogen in the middle point. It's just hydrogen. Then we use the hydrogen to ignite. Hydrogen we know easy to get ignitions. Then once hydrogen starts combustion, can ignite ammonia mixtures. Then we are doing this. We are doing currently for the CFD simulations. Use the OUL, use the dual fuel combustion. This you can find this in the internal combustion engine and the combustion chambers. How we running that combustion. So we can find we use a different a percentage of hydrogen to ignite the ammonia. We run a different technology, different simulation. Another side also we running the dual fuel for the this combustor for the jet engine or for the gas turbine engine. We run simulations, use the fluent. We have look how about the combustion take place in the jet engines. So far we're running most of this kind of research by the CFD. Also, we are build the test rig. We use these combustors We prove that hydrogen and ammonia, that we got the initial designs, and we can, from the compressor provide the compressed air. Then we got the combustion here. We can use laser, use optical or laser diagnostic. We can to research how the combustion, how the mixing, how the F ratio give influence on the combustions. So that's our current research. Apart from CFD, we are trying to get the experimental work. Okay, that's today 1 hour. I'd like to introduce probably more about use the general background information, why we need hydrogen, how we can use hydrogen for different area, how we can use another carbon-free fuel, ammonia, similar some way to support hydrogen or mix with hydrogen to running for the different application. Fuel cell, for the hydrogen fuel cell, definitely use the near pure hydrogen. But for the combustion sector, normally we can mix and hydrogen, some advantage, but some disadvantage. Ammonia, some advantage, some disadvantage. Joined together, we can get the use both advantage more. That's why for my today's talk, I talked more or less, not just hydrogen, also ammonia. Okay, thank you very much. And I finish here for my talk, and we can leave roughly 10 minutes for the questions.
Thank you so much, sir, for your valuable time and glimpse regarding all the topic regarding ammonia, hydrogen, and emission, everything. So we'll take question. So participant, kindly post your question in the chat box, or you can raise your hand for the question session.
But for that, stop to share. Back to the question sessions.
Hello, Professor. This is Vishwanath.
Hello.
Thank you very much for the enlightening session. So I have one question from your session. You mentioned that fuel cell vehicles are not advisable in UK and China related to their CO2 emissions, but it is good in the Norway. So my question is, how the fuel cell vehicles depends upon the environmental conditions? It will be same for every place now. So what is the analysis behind that?
Okay, actually, what we are doing, and actually, is we did a life cycle analysis for the CO2 or greenhouse gas emission for the fuel cell vehicle. Is currently the conditions. If in the future all the country got very clean electricity, definitely fuel cell is can get net zero. Our life cycle use the current condition is because in China, in India, our electricity not clean enough. Means we can't use clean electricity plus hydrogens. So in Norway, because their electricity were clean, they use the electricity by the water electrolysis can produce much clean the hydrogen. Then life cycle CO2 can very low. So, but in the future, for example, in India by 2070, all the electricity got the net zero, the greenhouse gas emission. Means in India, we can run in hydrogen fuel cell vehicle, no problem. Also zero CO2 emissions. Is my answer okay? Okay.
Yes, sir.
Okay. Yeah.
Sir, namaste from India, sir.
Nice to meet you. Yeah, Jagdish. Yeah.
Sir, thank you so much for your valuable time. Vishwanath sir, anything we can proceed?
And at the moment, from chat area, I can have some questions. Can we move to the chat area for give the answer? Or
why vehicle use only in PMFC?
Yeah, that's currently why because like the PEM fuel cell running low temperatures, only around 100 degrees, and also much higher power densities. Like Toyota, the Miras, the size probably is 500 millimeter the wide, and like a box, the fuel cell stack completed over 100 kilowatt, very powerful. Other type of fuel cell currently is difficult to get so high the power. And that's why currently on the vehicle side use a PEM fuel cell. Also some fuel cell like SOFC, they need running very high temperature. Start, stop were difficult. PEM fuel cell were easy to start and stop. Like we running the petrol car, we just switch on, switch off, that's okay. That's why we running the PEM fuel cell for the vehicles. Two reasons. One easy start, another is more powerful.
It's over to Professor Chalapati sir, head of the department. Sir, kindly.
Thank you. Thank you, Dr. Jivdesh. So I would like to thank Dr. Peng. Thank you for giving a wonderful keynote session. And it's a good start for us today, as it has started with a nice session from Dr. Surbi and then from you, Dr. Professor Peng. Soon we will be back to you, sir, after the sessions for any further contribution and collaboration between Anurag University and Thank you, sir. There are some doubts they are raising. The chat box, Jiptesh, please see. And Dr. Vishnu, sir, don't close the Zoom till the participants has given the feedback. Let's wait
Sure, sir. Sure.
till everyone gives the feedback.
Sure, sir. Sure.
Okay. Some more questions are there in the chat box.
Okay, thank you so much, Professor Chalapash. Yeah, thank you very much for invitation.
Thank you, sir.
Please share the links again.
Yes, sir. Yes, I'll do it.
Navya is having a doubt. Can you please raise the hand, Navya? We will unmute you. You can ask the question.
This is not there in the. Yeah, Nabia madam, are you there?
Yes, sir.
Yes,
Can you hear me?
Yeah, please.
Yes, very good.
Sir, I have a small doubt, sir. Sir, today in the current scenario, to replace the engines all at once, because we're having main issues like waste management and also due to economy, it is for us in the current scenario, for us, there is only one possibility to continue with the IC engines along with hydrogen, along with the diesel or petrol. As we observed that the detonation occurs when the hydrogen content of the total fuel exceeds 42%. So what are the measures you suggest us to overcome this current situation and increase the hydrogen energy content in the vehicle, sir? As it is not possible to completely demolish all the IC engines using the diesel and the petrol and increase the hydrogen energy content like hydrogen fuel cells.
Okay, if I get your question clearly, actually is currently for passenger car, we can running pure hydrogen to running hydrogen internal combustion engines, like the Toyota, like the I remember, and like the VW, they have developed technology, use the hydrogen running the passenger car engine, 100% hydrogen. Just from my slide, I give you one example. Is for example 40% or 20%. That's we talk about for the maritime, like a big ship. They use normally they take the mold ammonia to running the engines. So how we can mix the ammonia and the hydrogens for the different ratios, hydrogen and ammonia running the big engines. For the passenger car, definitely we can use 100%. Also for the vessels, for the ship, we can use 100% hydrogen. While with some part of the ammonia, that's in the beginning I mentioned, ammonia is easy to take by the boat, by the ship, by the different probably vehicles, because we can store more energy than hydrogen. Because for big like container vessel, very big, some 100,000 tons big vessel, if they take the whole energy by the hydrogen, need to take the big the size or volume to store so lot amount of hydrogens. So for the bigger internal combustion engine, we can run different ratios to running the hydrogen and ammonia. I'm sorry, I don't know my answer is meet your question or not. If not, you can repeat your question at some point.
Yes, sir. It's correct, sir.
I think you can
you, sir.
conclude maybe.
Yeah.
HOD sir, please.
Yes,
Fill
yes,
us.
we can conclude, and thank you, Dr. Peng.
Thank you very much. Yeah, Professor.
Thank you, sir.
Thank you, Dr. Panda. Thank you, organizer.
Thank
Yeah,
you. Thank you, sir.
Thank you.
Thank you,
Thank
sir.
you. Bye bye.
Bye, sir.
Bye, sir.
Thank you.
Bye.
We want all the participants to finish the feedback links before the session closes. Please fill the feedback links shared in the chat box.
We are on time, and we will keep the Zoom live for another 10-15 minutes, so that the people can
Yes, sir.
give the.
Check from the
No, I think we can stop the recording and stop the live stream.
we received only 60 responses. So I'm requesting all the participants kindly fill the feedback as soon as possible. So by the time we can close the session.